Sound can be transferred from one point to another. It is somehow similar to electromagnetic radiation. The main difference is that sound can pass only through matter and not through a vacuum as electromagnetic radiation can. In this lecture, I will focus on introducing ultrasound application as a diagnostic tool, given that it can be focused into a well-defined beams in probing the human body to form a medical image. Let's start. This is the outline of this video lecture. Let us start by discussing what is sound. Sound is a mechanical energy transmitted by pressure waves in a medium. Mechanical energy, meaning it requires some form of physical movements of the molecules and particles in a given medium. Sound waves only exist in media containing particles and cannot travel through a vacuum. If the frequency of the sound waves is greater than 20 kHz, which is the maximum limit for the human hearing range, this is termed as the ultrasound. In diagnostic ultrasound, it involves frequencies in the range of 1 MHz to 20 MHz. For medical ultrasound, the source of sound waves is a piezoelectric transducer, as shown here, which is used for medical ultrasound. It produces sound waves in the tissue in contact in response to an electrical impulse. It is possible to emit very high frequencies required in an ultrasound examination. Commonly, the speed of sound in air is about 330 meters per second, which depends on the pressure and temperature of air. Sound waves is considered longitudinal as well, which means that the particle displacement is parallel with the wave propagation direction. This back and forth displacement of the source squeezes and pulls the particles in the medium, creating compressions and rarefaction parts. The speed of sound in a medium is determined mainly by the characteristic of the medium. Longitudinal sound waves in either liquids or body tissues is expressed as this equation C is equal to the square root of B over rho, wherein B is the Box modulus, which is just a measure of the stiffness of the material, or it is the resistance of the material to compression over mass density rho. Let us focus now on transducers. Transducer refers to a type of device that converts signals or energy from one form to another. Ultrasonic transducers convert acoustic energy to electrical signals, as shown in my drawing at the left, and electrical signal into acoustic energy, as illustrated this time at the right drawing. Therefore, it acts both as a detector and as a transmitter. These are the speed of sound in some non-biological media that may be useful in designing the ultrasound transducer or in designing a QC material for ultrasound imaging. The sound speed in biological media is an important parameter in imaging applications. In this table, we have some of the approximated sound speed in different human tissues. It can be observed that for lung tissue, which is known to be not compact and composed of air-filled alveoli, has the lowest speed of sound. Tissues that are mostly of interest in ultrasound imaging, that we will refer later as soft tissue, is in between of fat and muscle. Sound speed in bone tissue is the highest in the table, given its compact structure, thus higher Box modulus. The average speed of sound in soft tissue, not considering the lung tissue, is approximately 1,540 meters per second. Diagnostic ultrasound measuring algorithm is usually based on this approximated value. Now let's talk about the wavelength and the frequency. Sonographers select the ultrasound frequency when they choose a transducer or a probe control setting. This is shown on the right for both images, the one with red circles. The wavelength in ultrasound physics is important because it is related to the spatial resolution of the image that will be produced. Wavelength is said to be the acoustic meter stick, wherein objects are measured in terms of their size relative to the wavelength. Acoustic pressure amplitude is important to quantitatively describe the strength of a sound wave. It is defined here as the maximum change in the pressure relative to the ambient conditions in the absence of sound wave. This is related to loudness when we are talking about audible sounds. To quantify the intensity to a certain location, we have this expression, I is equal to P squared over 2 rho C, wherein P is the pressure and rho is the mass density, C is the speed of sound. In addition, this quantity is useful when talking about possible biological effects of ultrasound, such as the production of heat during ultrasound attenuation, generation of tiny bubbles called cavitation, and non-cavitation effects such as displacement of particles in the medium. Ultrasound images is mainly influenced by the amplitude of the returning or reflected echoes. This is affected by a quantity called acoustic impedance or characteristic impedance. It is expressed as Z is equal to the product of the medium's density, rho, and the speed of sound, C. With the SI unit for mass and speed, we have this unit 1 kilogram per square meter seconds as the final unit, and commonly referred to as rails. In the table here, we have the acoustic impedance of some tissues wherein the lung has the smallest impedance and the skull bone has the highest value. When an ultrasound beam is incident to a certain interface formed by two different materials, as shown in the drawing below, for a smooth interface between the first and second tissue with different acoustic impedance value, a fraction of the energy will be reflected and the remaining energy will be transmitted. The amplitude of the reflected wave depends on the acoustic impedances of the materials. If the beam is in perpendicular incidence on a wide, smooth flat interface called the specular reflector with dimensions greater than the ultrasound wavelength, the ratio of the reflected to the incident pressure amplitude is given by this formula. So we have Z2 minus Z1 over Z2 plus Z1. This is called the amplitude reflection coefficient, wherein Z2 is the acoustic impedance on the distal side of the interface and Z1 is the impedance on the proximal side. We can also express ultrasound reflection in terms of the intensity reflection coefficient, shown here with the acoustic impedances squared. Now, if we try to calculate the reflection coefficient for muscle-air interface, we will get a value of negative 0.99. It means that the incoming beam is almost completely reflected, with the negative sign referring to its phase. Thus, only a small fraction of ultrasound will be transmitted beyond this type of interface, which is a disadvantage in ultrasound imaging. This is the reason also why we use coupling medium like gel or oil between the ultrasound transducer and the patient during diagnostic procedure. Overall, reflection of sound beam occurs when the beam is incident to an interface with different acoustic impedances. Let us now consider the case when the incident beam is not perpendicular relative to the surface of the interface. As illustrated in the drawing, the reflected beam travels at an angle theta r, and by law of reflection, this theta r is equal to theta I. Then refraction or bending, following the Snell's law that I think we're familiar with of the sound beam, is also observed as it traverses medium 2. This is similar with how light waves reflects and refracts. For sound waves to refract, it must be incident on the interface at an angle, not perpendicular, and the speed of sound must be different on the two media. In reality, not all the interface inside the human body can be considered as specular or smooth surfaces. Some examples of rough surfaces or diffuse reflectors are walls of the heart chambers, or it can be a small blood vessels. The reflected sound waves from a diffuse reflectors is illustrated in my drawing here at the right. These reflected waves travel in different directions and usually weaker relative to the reflection from a smooth surface. Next, let's discuss echo from scattering. Acoustic scattering is the source of echo signal important in ultrasound imaging. It generally refers to reflection of sound waves from small objects. Shown here in the drawing is an illustration of scattering due to small reflectors. Modern ultrasound machines are sensitive enough to detect small signal amplitude due to scattering. Changes in the signal amplitude, as illustrated by the detected echo signal drawing, produces brightness differences on the ultrasound image. The brightness of the structure can be clinically described using the term hyperechoic or brighter region and hypoechoic darker region. Echo signals depend generally on the number of scatterers, uh, change in acoustic impedance, size of scatterer, and ultrasonic frequency use. In the picture, we have 3.5 megahertz ultrasound tissue harmonic imaging for the four chambers of the heart. In describing intensities and power levels in medical ultrasound, decibel notation is utilized. That allows us to compare two signal levels. This is used in discussing attenuation and amplification of sound signals. Shown here are the expressions first for relative signal level and relative intensity level in decibels. Note that the intensity is proportional to the amplitude squared. That's why we have 20 here. This is useful in compressing large differences in amplitude or intensity. Example is the ratio, let's say, of two intensities can be about 10,000 or even a million. One thing to note about here at the right is the decibel notation in 3 decibel rule. A 3 decibel increase is the intensity multiplies to the intensity by 2. If there is a decrease by 3 decibel in intensity, the intensity value will be divided by 2. And this is useful in adjusting the amplification or gain of the instrument. Sound waves get attenuated as it traverses the medium. And this is generally described as a decrease in amplitude as a function of distance. Some sources of attenuation includes reflection, scatterer, and absorption that produces heat. We have this attenuation coefficient which describes the degree when sound waves attenuates in decibel as it traverses a unit distance in centimeter. This is illustrated in my drawing at the left with the graph of echo amplitude detected by transducer as a function of distance. The attenuation generally increases with increasing frequency. Thus, higher frequency means poor penetrability. We can just image well superficial parts given a high frequency. But note also that higher ultrasound frequency means higher spatial resolution or detail of the image. Overall, this is about the compromise between penetrability or imaging deeper structures and spatial resolution. And that's it for this lecture. Hi, if you have learned something in this video and you like my content, please consider subscribing my YouTube channel, JP Academia. See you in the next video.